In this video, we will do another hypothesis testing problem on the mean using the critical region approach. So here's the scenario. Unfortunately, arsenic occurs naturally in some groundwater. A mean arsenic level of 8 parts per billion is considered safe for agricultural use. A well in Texas is used to water cotton crops. It's tested on a regular basis for arsenic. A random sample of 37 tests gave a mean of 7.2 parts per billion of arsenic. Based on previous studies, assume the population standard deviation of arsenic level is 1.9 parts per billion, and at a 1% level of significance, should we believe the claim that the mean level of arsenic in this well is less than 8 parts per billion? So we're going to run through the 6-step process using the critical region approach. Again, step 1 is defining your hypotheses. So first, let's write down what the claim is. So should we believe the claim that the mean level of arsenic in this well is less than 8 parts per billion? So that claim is that mu is less than 8 parts per billion. And that is our claim. Again, you really want to write down the fact that it's a claim because it's going to play an important role when we get to step 6. Now, again, don't worry about what's the null hypothesis or what's the alternative hypothesis yet. Let's first write the complement of this. The complement of mu is less than 8 is mu is greater than or equal to 8. Once we've got both of them down, then we can assign one to be the null hypothesis and the other to be the alternative hypothesis. And don't forget the null hypothesis is always the one with the equality. So h sub 0 is the mu is greater than or equal to 8, whereas the alternative hypothesis, h sub a, is mu is less than 8. So in this scenario, unlike the previous problem we did, the alternative hypothesis ends up being the claim. Again, the null hypothesis is not always the claim. Sometimes it is, sometimes it is not. Step 1 is complete. Now, step 2, we need to note the level of significance. This is at a 1% level of significance, so this is a pretty strong level of significance. There's only a 1% chance that we're going to make a type 1 error when making our decision here. Step 3 is then to determine the tail of the test and the type of test. Well, the tail of the test is determined by the alternative hypothesis. So let's look at that. You've got mu is less than 8. So if you've got mu is less than, then you're dealing with a left-tailed test. So we are doing a left-tailed, and we need to decide, are we doing a t-test or a z-test? So if you go back up here, notice that this says, assume the population standard deviation of arsenic level is 1.9 parts per billion. That means to assume that sigma is equal to 1.9. That's the population standard deviation. So in this scenario, we may be using a z-test. Now, in order to use a z-test, we need to know the population standard deviation, which we do. But we also need to have either sample sizes greater than or equal to 30, or we need to know that the data is normally distributed or at least approximately normally distributed. And technically, we've got this right here, which is the sample size. So we have n equals 37, which of course is big enough. It's greater than or equal to 30. So this means we are going to be doing a z-test. We are doing a left-tailed z-test. So in step 4, we're now going to draw the critical region graph. And of course, this is the standard normal distribution now because we're doing a z-test. So these are z-scores along the axis, the horizontal axis. And as you already know, the standard normal distribution has a mean of 0 and it's symmetric. And again, it says in step 3 that we're doing a left-tailed test. So I'm going to shade in the left-hand region. So this is going to be our rejection region. How big is that rejection region? Technically, we didn't need to worry about that when we did the t-test, but it is true that the size of the rejection region is what alpha actually is. So this is 1% of the entire area, that rejection region there shaded in blue. We didn't necessarily note that with the t-distribution because we didn't really need to. We could jump right to getting the critical values, but now we actually have to do some work, extra work to get the critical values because the standard normal distribution table does not give you the critical values. Remember, the standard normal distribution table, in the heart of the table, what you get are areas to the left of a particular z-score. So ultimately, to find this critical value right here, we need to find the z-score that has 1% of the area to the left of it under the standard normal distribution curve. If you look in the heart of your standard normal distribution table, you'll see the closest area to 0.01 is 0.0099, and that is associated with the z-score negative 2.33. Means this critical value right here is negative 2.33. Now that we've got our critical region graph fully labeled, we now need to go over to step 5, where we will compute our test statistic. Since we're doing a z-test, we're going to compute the z-test statistic. Well, the z-test statistic, as a reminder, is equal to x bar minus mu over the ratio of sigma to root n. X bar is the sample mean. And we saw here a random sample of 37 tests gave a mean of 7.2 parts per billion. So X bar is 7.2 minus mu is the hypothesized mean. So that's this number referenced over here. So mu is 8 over sigma we had was 1.9 divided by the square root of the sample size in this case is 37. And if you plug this thing into your calculator, don't forget that you need to make sure you put parentheses around the numerator and around the denominator. If you do that, you get approximately negative 2.56. Remember, we are not done step 5 yet. Step 5 consists of computing the test statistic and then also deciding on whether you're going to reject or accept H naught. Well, we've got to see exactly where this test statistic falls in our graph. So negative 2.56 is less than negative 2.33. So that's going to put us over here in this shaded region, which is our rejection region. So we are going to reject H naught. So as part of step 5, write in that you're going to reject H naught. Now that doesn't necessarily mean we're going to reject the claim. Step 6 is where we make that decision. So the test says to reject H naught. In step 6, we need to look back at step 1 to see what the claim was. Well, the claim was the alternative hypothesis. The test says to reject H naught, but the claim is the alternative hypothesis. That means we should do the opposite of rejecting it. We should accept it. And really, again, by accept, I really mean fail to reject, since accept and fail to reject are not really exactly the same thing. It's just easier to simply say accept. So that's what I'm going to write. So we are going to accept the claim. And the claim, again, is that the mean level of arsenic is less than 8 parts per billion. So don't forget, you want to write the level of significance in here. At 1% level of significance, which is strong, at 1% level of significance, we accept the claim that the mean arsenic level is less than 8 parts per billion. We've now completed another example using the critical region approach for hypothesis testing on the mean.